All right, we're going to start our new unit on force and dynamics um, by talking about Newton. Newton's laws. You may remember from the first day that we call sort of physics of everyday objects that aren't moving super fast or moving super slow Newtonian physics, and that's why, because these three laws are really foundational to the way that we describe physical behavior. So dynamics concerns the relation between motion and force. And we can think of force as a push or a pull. Um, the technical definition of it essentially is the thing that causes motion. So that's not very helpful to us. Um, but there are a number of different kinds of forces. We have contact forces, which, as you imagine, involve the contact between two surfaces. So friction, um, which we're familiar with. Spring forces, when you press in a spring and it pushes back. An applied force really is a catch-all term for any kind of force that is directly applied to something, like if I'm, lifting a bag up or pulling a horse by its rein. Um, any of those are seen as applied forces. And then we have non-contact forces, such as gravitational force, which we've dealt with but haven't really talked about as a force, and things like electromagnetic force and a bunch of um, uh, molecule level forces that we're not going to deal with in this class. The foundation of dynamics are Newton's three laws, and here's Newton in his old age over here, so he doesn't have his glorious wigs on. Newton apparently wasn't a very nice guy, but he came up with some important ideas. Um, or he came up with some important ideas while other people were also exploring those important ideas. And he got credit for them. Anyway, that's neither here nor there. Um, but these all explore the interaction between force and acceleration. So let's take a look at those three laws. The first law says that an object will stay in motion unless acted on by a net external force. Um, Now that seems in some ways counterintuitive to us because we know when we kick a ball across the field, right? I apply a force with my foot to the soccer ball. It stops. Okay. Um, the reason it stops is friction, and so that tends to be a kind of invisible force to us. So that ball, which is rolling along there, we think of it as not being acted on by a net external force. But there is, in fact, some external force there. The forces of drag, which is it trying to move through the air, forces of friction with the ground, which are not all that substantial because it's rolling, but if it's rolling across grass or something, there's going to be some frictional losses there. Um, and so there is kind of an external force there. So our experience tells us that when we move something, it stops on its own. Um, but that experience fails to recognize that friction is actually active there, that drag is active there. But an object in motion, like say in space in a vacuum, um, if it's not bent by some gravitational external force, it will continue in a straight line uh, forever. A couple other things that are difficult about this. One is net force. What does that mean? Well, that means that more than one kind of force can be acting on an object at any given time. So when I'm throwing a ball up into the air and it's still in my hand, uh, there are multiple forces acting on that. My hand is an applied force that's pushing it upwards. Um, Gravity is a gravitational weight force that is pulling it downwards. Uh, Drag is air that's being moved by the ball as I try to accelerate, and that's applying a force on the ball as well. So all of those things are happening at once, and what we want to know is when we add up all of those forces, um, what is the direction of the force and what is the magnitude of the force? Okay, so you can start to see that 2D stuff coming in, right? Is it going to be, is the net force upward? Is my hand strong enough to overcome gravitational force? If it is, then the ball will accelerate upwards. But if it's not, then it won't. So you have to, force is summative. What that means is we have to add them all up together and see what the total of the forces does. And finally, it has to be an external force. And so that external force means something outside of the system. So if, let's say you are in a rolling wagon, I'm blanking on a good example here. You're in a rolling wagon, right, with your friend. And you're worried because your wheels are frictionless and you're going to roll into a lake. And so you and your friend start trying to push the wagon from the inside. You can't. Why can't you? Because you're an internal force. And as we'll find out in a minute, that internal force is always going to balance itself. So if I'm inside the wagon and I'm pushing backward on the wagon is also simultaneously pushing forwards on me. And that means as a whole, nothing is making that, there is no force on the outside that is going to cause that wagon to slow down because you're all part of the same system rolling towards the lake. And so you're going to get wet. So we need to talk about a net force, and we need to be conscious that those forces have to be external to the system that we're trying to describe. Okay, we'll get more into that when we start dealing with individual problems. Second law, and this is the one that we're most familiar with. I'm going to read it to you just to make you laugh. An object experiencing a net force will have an acceleration proportional to and in the direction of the net force and inversely proportional to its mass. Okay, I'm never going to read that sentence to you again, and I'll never say it in class. Instead, what I'll write is this. Okay, this says exactly what that says. All right. The more common form is this one. So this is F equals ma. So this is Newton's second law. And what it tells us is that the larger that net force is, and that's what this sigma means. That means the sum of forces. So this is the net force. The larger the net force is for a given mass, the more it's going to accelerate. Okay. And for the same sum external force, if I change the mass, if I make the mass less, it's going to accelerate faster, right? So in the example over here, this poor fella, he's applying force F to a basketball. It's going to accelerate pretty quickly, right? Because this term is going to be small, and that allows this term to be bigger. But when he's trying to push the car and he's using the same force F, right? So this stays the same. That means when this is really big, to have this product equal this, that acceleration is going to be really small. Okay, so I can apply the same force to something with a lot of mass and with less mass, and that's going to change the amount of that it accelerates. That's the second law in a nutshell, and it's a direct link between force and acceleration. So this is the equation that we're going to use most in these next couple of days in class. And really for the rest of the term. This comes up all the time. All right, so what does this mean and why is this interesting? Well, this is what the two things I want you to make sure that you always are aware of. And so repeat after me. A non-zero net force always creates acceleration in an object. Okay? If you have a non-zero net force, when you add up all of your forces, if that force vector is not zero, then you're going to have an acceleration in your object. The second thing you need to repeat after me is all acceleration is caused by a non-zero net force. Are you repeating? Repeat that. Anything that is accelerating has some kind of non-zero net force acting on it. Okay? So we always have to think through this. In a given situation, we have to ask ourselves, well, if there's acceleration, then there must be a force. And if I can't identify a force, then you might have to rethink whether it's accelerating or not. Okay, but these things, a non-zero net force and acceleration, are directly tied to each other and are always true. Okay, that tie is always true. The forces of, or the units of force in MLT terms are MLT to the negative 2, or ML over T to the second. And in metric units, that's a Newton. So what does a Newton look like? Well, let's look at Newton's second law, force, right? We know force has to have units of force. So this has to have units of force, right? Because dimensional homogeneity tells us that all of these are equal signs, so they all have to have the same units. So let's figure out what these units are. Kilograms times acceleration, which we know is meters per second squared. And so this has units of kilogram meters per second squared, and that is a Newton. Okay, go back to MLT. We have kilogram times meters length over seconds times squared. All right. So when you do problems, and this is really crucial and helpful, if you start off in metric base units, which are kilograms, meters, and seconds, and you stay in base units, in other words, if you have kilometers in your problem or hours in your problem, you have to get into base units. If you stay in base units, your answer is going to be in newtons. And I stress this very strongly. Just unless it's really some other reason to stay out of base units, always put your problems in base units, and then your answers, you'll know what the units are. All right, the third law. So first law, something that is moving is going to keep moving unless it's external forces acting on it. The second law connects force. The sum of forces, or the net external force, is going to be equal to mass times acceleration. The third law says that any two interacting objects exert equal forces of the same type in opposite directions upon one another. Okay, what does that mean? In equation form, it means this, that the force of 1 on 2 is equal to the vector opposite of the force of 2 on 1. So in this picture over here we have an interaction between an object. These are our interacting objects. The feet are pressing on the wall, and the wall is pressing on the feet. Okay, so the force of the feet on the wall, which is pressing in the rightward direction, is going to be equal and opposite to the force of the wall on the feet. Okay, what does that mean for acceleration? Well, is the wall going to accelerate? It's very heavy. It's the Earth. So it will have some acceleration. It has a net external force on it, but it's going to be so tiny as to be completely insignificant. But the force of the wall on the feet is what propels the swimmer forward. Okay. So this is what is called a Newton force pair, or a force pair. So the swimmer here and the wall we would call a force pair. And one of the things that throws people off is you say, well, there are two forces here. Isn't our net external force going to be 0, right? We're going to sum these two forces and find 0, and that means there's no acceleration. And the answer to that is no. That is not what happens here. And the reason that doesn't happen is that these forces are acting on different objects. This force is acting on the swimmer. This force is acting on the wall. Okay, so they don't cancel because they're not acting on the same object. What are the forces acting on this swimmer? Well, there's the force of the wall on her feet. There's the force of the water against her body, which is slowing her down. Those are the external forces. You might say, well, what about the force of, her arm muscle pulling on her arm? That's an external force, right? Or the force of her thigh pushing out here. Those are internal forces rather, and we're not going to count that within that what we call a system uh, because they're not external forces. The external forces are the drag of the water and the wall on her feet.